This video is brought to you by mywayteaching.com.
So in this part, let us see one more simple problem, that is example 2. See, which of the following functions of time represent? The first one is a periodic and B non-periodic motion. So give period for each case of periodic motion, and here W is any positive constant. So we should take each one of these values, or we can say the cases, and we should find it which one represents the periodic motion and which one will represent the non-periodic motion. Okay, so let us find the solution by for the first one. So the first one is sine omega t plus cos omega t, isn't it? Okay, this is a periodic function. It can also be written as square root of 2 sine omega t plus pi by 4, isn't it? See, now we can write it as square root of 2 sine omega t plus pi by 4 plus 2 pi, isn't it? And in general, we can write it as square root of t. We can take w common, t plus 2 pi by w plus pi by 4. So this is what this equation represents. It is nothing but this equation is a periodic equation, and with the periodic time of the function 2 pi by w. Okay, now considering the second equation, that is given by sine omega t plus cos 2 omega t plus sine 4 omega t. See, this is an example of a periodic motion, because here it can be noted that each term represents a periodic function with a different angular frequency. So here it is omega t, this is 2 omega, and here it is 4 omega. It goes on. Since period is the least interval of time after which a function repeats its value, sine omega t, this sine omega t, it has a period that is equal to t naught 2 pi by omega w, and cos 2 omega t, the second one, again it has a period that is given, okay, that is pi by omega is equal to t naught by 2, and the last one, that is sine 4 omega t, two pi by 4 w t naught by 4. So the period of the first term is a multiple of the periods of the last two terms. So the smallest interval of time after which the sum of the three terms repeats is t naught, isn't it? And we can say this is a periodic function with a period equal to 2 pi by w, isn't it? So coming to the third part of the question, that is e raised to minus omega t. See here, this function is not periodic because this exponential function, it decreases monotonically with increasing time, and even it tends to zero as t tends to infinity. Okay, so it never repeats its value. So this is not a periodic function, we can say. Okay, and coming to the next part of the question, that is log omega t. See, this function also it increases monotonically with the time t. So it never repeats its value, and again it is not a periodic function. Okay, and it we can say that it may be noted that as t tends to infinity, this log omega t, it also diverges towards infinity. So it cannot represent any kind of physical displacement. So now let us study what is simple harmonic motion. You just consider a particle which is oscillating back and forth. As you can see in this figure, this is a particle which is continuously moving back and forth about the origin of an x-axis between the limits, that is plus a and minus a. And this oscillatory motion is said to be simple harmonic only if the displacement x of the particle from the origin varies with the time. As so if it varies from the origin as a function, that is x of t is equal to a cos omega t plus pi, where a, omega and pi, all of these are constants. So we can say a simple harmonic motion is not any periodic motion, but one in which displacement is a sinusoidal function of time. So you can see in this figure, okay, it shows what the positions of a particle executing simple harmonic motion are a discrete value of time, each interval of time being t by 4, where t is period of motion, isn't it? So you can see t is equal to 0, t by 4, t by 2, t by 4. So here in this figure, you can see here a sequence of the shots which are taken. Position of a particle, okay, which shows the position of a particle as it oscillates back and forth about the origin along an x-axis between the limits plus a and minus a. So that was the this figure description, and here in this figure you can see the location of the particle in simple harmonic motion at the discrete values, that is t is equal to 0, t by 4, t by 2, 3 t by 4, t and 5 t by 4, and even the time after which the motion repeats itself, that is t. You can see after this time period t, that motion again it repeats itself. T will remain fixed no matter what location you choose as the initial location, and the speed is maximum for zero displacement and zero at extremes of motion. Okay, and in the coming figure, that is in this figure, you can see the it plots the graph of x versus t, that is displacement versus time, and the quantities again a, w, and pi, which characterize a given simple harmonic motion. They have standard names. So what we call those things? See here, x of t, we call it as what? Displacement x as a function of time t, isn't it? And a is amplitude, and w is angular frequency, and wt plus pi, we can call it as phase, and pi is nothing but phase constant. And the amplitude A of the simple harmonic motion is the magnitude of maximum displacement of the particle. Okay. As the cosine function of time varies from +1 to -1, the displacement varies from plus a to minus a. And two simple harmonic motions may have same w and pi but different amplitudes a and b, that you can see in this figure. Here two simple harmonic motions, they have different they have same w as well as pi, but their amplitudes are different. You can see this, the amplitude a for the first one and amplitude b for the second one, isn't it? And when this amplitude is fixed for a given simple harmonic motion, yeah, even the state of motion, which means the position as well as velocity of the particle at any time t, it is determined by the argument, that is wt plus pi in the cosine function. And this wt plus pi, that is nothing but the phase, isn't it? Time dependent quantity, which is also called as phase. And the value of phase, no, phase at t is equal to 0 is pi, and we call it as phase constant. And when we know the amplitude, pi can be determined from the displacement at t is equal to 0. By putting t is equal to 0, we can easily determine the pi. And two simple harmonic motions may have the same amplitude a as well as w, but they can have different phase angle, as you can see here. So the first one having the phase 0 and the second one is having the phase of minus pi by 4, isn't it? Yes. And finally, the quantity w that is angular frequency, can be seen to be related to the period of motion t. Taking for simplicity, that means we take pi is equal to 0 for simplicity, and we can write x of t is equal to a cos wt. And since the motion has a period t, x of t is equal to, since it is periodic, this is equal to x of t plus t, isn't it? So we can write a cos omega t is equal to a cos omega t plus t. And now the cosine function is periodic with period 2 pi. It first repeats itself when the argument changes by 2 pi. So Wt plus t is equal to Wt plus 2 pi. So this W is nothing but what? Yes, that is nothing but angular frequency. And its SI unit is radians per second. And the frequency of oscillation is simply 1 by t. W is 2 pi times the frequency of oscillation. See, again you can see in this figure there are two simple harmonic motions. They have same amplitude as well as phase constant pi but different angular frequency. Okay. See, the curve B is as half the period and twice the frequency of curve A. This one is curve B and this sky blue is curve A.